Okay, welcome back to fuzzytutor.com. Today we're going to talk about resolving component vectors, okay? First of all, we talked about vectors and scalars. Vectors have magnitude, so like velocity, force, distance, and direction, where scalars just have a magnitude. So let's imagine a scenario where someone has a box, and this box is sitting in the middle of the floor. That's a terrible box, I know. So this person is pushing the box, right? And then another person is pushing from this side over here. So we have one force vector going this way, and one force vector going this way. Let's assume they're both 10 newtons of force, right? And then he's pushing 10 newtons of force. So the box is going to go somewhere in between the two, right? That's the direction it's going to ultimately go. So we use vectors to isolate exactly what direction and with what magnitude something's going to move or react or behave. So that's just a really simple example of how we can use this. So what we're going to do is we're going to talk about a vector. Let's first draw our Cartesian graph, a really simple one here. So we have an x-axis and we have a y-axis, okay? And then we have this vector, we'll call it resultant vector. And it's the result of the components that we're looking for. So every vector has a set of component vectors, two component vectors. One, and this is a two-dimensional concept right here. So here's a 90-degree angle between this parallel to the y-axis. So this is our r sub y, right? Because it's the component of r along the y-axis. And here's our r sub x because it's a component of the r vector along the x-axis here, right? So let's talk about the Pythagorean theorem with regard to the r vector. So this r vector is equal to c as far as the Pythagorean theorem is concerned. So we have a squared plus b squared equals c squared, right? And c is going to be equal, therefore, to the square root of a squared plus b squared. Okay, that's pretty simple, pretty straightforward, right? Because if a squared plus b squared equals c squared, that means if we take c squared, it is equal to the same as just a squared plus b squared, which we have right here. So I could just have written this as c equals the square root of c squared, right? It's the same. It's the same as this. So that's what that's about. Now let's back up for just a quick second. So Pythagorean theorem, a squared plus b squared equals c squared. So that's handy because we are, equal c where a squared plus b squared equals c squared, and c is equal to the square root of a squared plus b squared. I probably shouldn't have erased that. So we'll keep that up there just as a side note. So we're dealing with a 90-degree triangle, right? So Pythagorean theorem is definitely in play here. We know the relationship between this x-axis and the resultant vector is angle theta, and we know that theta is equal to 50 degrees. We know the magnitude right here is 175 meters. So r is equal to 175 meters, right? So that vector right there is a magnitude of 175 meters, and it's at a direction 50 degrees in relationship to x. So what we want to figure out is the magnitude of the component vectors. So r sub y is equal to r times sine theta. Okay. R sub x is equal to r multiplied then by cosine theta. So remember that sine, cosine, and tangent are nothing more than ratios. And remember, ratios are the same as percents, are the same as decimals, are the same as fractions, are the same as division, right? So all sine is a rate of opposite over hypotenuse divided by hypotenuse, right? And opposite, we're talking about opposite of theta. So there's theta, so directly opposite of theta is right here. Here we see cosine is a rate of adjacent over hypotenuse. And adjacent means adjacent theta, so that's right here, adjacent to the theta angle. Tangent, it's kind of clumped in there, we'll put it right down here. So tangent is opposite over adjacent. So this over this gives us tangent, right? This is opposite theta, this is adjacent theta. Now, these are our trigonometric functions. So these are trig, and I'm just going to write functions, right? Trig functions, right here. Now, we can add another angle here, and we'll call it alpha. You see this square, that tells us 90 degrees, right? So we know we're dealing with a 90-degree angle. It's a right angle triangle, we talked about that. We know that, according to the axioms of geometry, that there are 80 degrees within a triangle. So we know that 90 of those are here, and 50 of those are here, right? So we need this plus this to equal 90, so that we have 90 plus this 90, right? So in order to do that, we know we have 50 degrees, plus alpha has to equal 90 degrees. We just use basic algebra. We're going to isolate that alpha by subtracting here, right? What we do to one side of the equals, we have to do to the other side of the equal sign to keep that a true statement. So alpha is equal to 90 minus 50, which is 40 degrees. So we know alpha is 40 degrees. We know that theta is 50 degrees. We know that r is 175 meters. We know that r sub y is equal to r multiplied by sine theta, and that r sub x is r multiplied by cosine theta. So you're going to need to know, these are some new rules you're going to have to throw in your toolbox. Some new tools, I should say, that you need to throw in your new rule box. There you go. And so now what we're going to do is just go ahead and plug and chug. So we have r sub y is equal to 175 meters times sine 50 degrees, which comes out to 134 meters. There's our meters, right? That's our unit of measure, right? So that's the magnitude of this guy right here, 134 meters. So now we have r sub x, let's look at that, r sub x is equal to 175 meters times cosine of theta, which is 50 degrees, which equals 112.5 meters, so 113, right? So 113 meters for this right here, right? And there you go. And you can figure out the tangent by, 134 over 113, and get your tangent. So you can see the relationships and how they work. So there it is. That is how you resolve the component vectors of a vector. So every vector can have a right angle of component vectors built off of it. And then you'll see in the next video how we'll take the component vectors of multiple vectors being applied to one situation and then find out what the resultant overall vector is of all of those vectors by using these component vectors. So the main thing we need to take away from this is make sure that we understand that SO, CA, TOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. We know that there are 180 degrees within a triangle. We know that right angle triangles allow us to use the Pythagorean theorem. And we know that the component vectors, so the y-axis component vector is the original vector, or the resultant vector as we called it, multiplied by sine of theta. We know that the r sub x is the resultant vector, or the original vector, multiplied by cosine theta. And again, the reason it's an original vector and a resultant vector is it's the vector we started with. So by that measure, it's the resultant vector. But I call it the resultant vector because we're isolating its component parts, which means that it is the result of these components as much as these components are the result of it, right? So I just call it the resultant vector of these components. So it's not as confusing as you might have thought a second ago. Alright, thanks for coming to fuzzytutor.com. Make sure you check us out again and check out the next video so you can move on to multiple vectors being combined together.